this video, we're going to look at how gates are combined to create circuits. But before we start, let's look at the concept of transistors. I'm looking on page 102 of your textbook. Now, the very first paragraph says that gates are made of one or more transistors and defines transistor as a device that acts depending on the voltage level of the input signal. Either as a wire, it's going to go ahead and conduct the electricity, or as a resistor that blocks the flow of electricity. A transistor has no moving parts, yet acts like a switch. This is very important. If transistors were mechanical, then you wouldn't be able to have the speed that computers have. Transistors are made out of semiconductor material. So it's neither a good conductor like copper wire, nor is it a total resistor like rubber would be. It's in between. And it's usually made out of silicon, and that's where we get the term Silicon Valley from. Let's move down to the third paragraph. A couple of basic concepts of electricity is that there's a source, and it could be a battery. In my laptop, it's a battery, or on my desktop, it's an outlet in the wall, and that's our source. In addition, you may know the concept of grounded, and so if something is grounded, then it allows the flow of electricity to go through an alternate route to the ground, literally, where it can do no harm. So here is a transistor, a schematic of a transistor, and here's our source. The source is always on. This is the battery, or this is the outlet source. Here is a connection that can be made, call it the base, and then here is the ground. Now, if the connection is made, you notice that the voltage will flow towards the ground, and what's going to happen to the output? There's not going to be much output. So when this base is on, or 1, the output is 0. But when the base is off, then there is not a connection. So the base is 0, it's off. There is not a connection here. This gate, if you can think of this gate as swinging open and close, this is the switch right here. And yet there's nothing but pure electricity that's making this switch close and open. So when this switch is open, the source cannot flow to the ground, so then the source has to flow through the output. Okay, so when the base is 0, our output is 1. If you would like to learn more about how transistors exactly work down to the atoms and the electrons, I recommend that you watch this video, How Does a Transistor Work? A lot of the concepts that we've talked about, including Moore's Law, is addressed in this video. It's very entertaining and interesting to learn video. Okay, let's continue with the concept of circuits. So we know what a transistor is. Transistors then are combined to make up our gates. So you see here that the NOT gate is simply one transistor. If you recall, 1 in is a 0 going out. A 1 in at the base was a 0 going out, and vice versa. If we had 0 in and we had 1 going out, I didn't know if you thought about it while we were talking about transistors, but if one transistor creates a NOT gate, and notice that we have 2 other gate choices here. The NAND gate is simply a series of transistors in sequence. NOR gate is a series of transistors in parallel. I do not expect you to memorize these structures here, but I do know that a NOT gate is just made out of exactly one transistor. Transistors combine to make gates. Gates combine to make circuits. 2 types of circuits we'll look at are combinatorial circuit. And so in a combinatorial circuit, if you tell me the input, I can logically deduce the output. A sequential circuit, however, the input alone is not enough information to determine the output, because you also need to know the existing state of the circuit. And just like gates, how do you notate a circuit? Well, the 3 same notational representations: Boolean expressions, logic diagrams, and truth tables. So here we have a circuit. let me explain what's going on here. We're having input A is actually splitting. So input A is going into this AND gate. It's also going into this AND gate. So input A and B will be processed by this AND gate. Input A and C will be processed by this AND gate. The output of A and B here is being called D, and that output plus the output of A and C, which is being called E, then will be processed by this OR gate. So let's take a look at what's happening. Well, the first thing that's happening is A and B at about the same time. A and C is happening. So I've written this gate here as a Boolean expression as we did earlier, and I've written this one as a Boolean expression as we did earlier. Now the output, as I mentioned earlier, of these two, well, you could think of this as D, and you can think of this as E, and we're ORing that, okay? So instead of ORing D and E, I'm going to place an OR right here, and so you see this entire logical diagram can be expressed in a Boolean expression as A and B or A and C. Our authors short-circuited this, so this expression are saying the same thing, A and B. So without the operation there, the default Boolean operation is to do an AND. So this is saying A and B, this is saying A and C, this is saying we're ORing it. I think the way I express it's a little bit more readable. Now remember that the third way to notate a circuit is with the truth table. So I'm going to show you how to take this logic diagram and create a truth table from it. So the first three rows are going to be my inputs, A, B, and C. So the simplest way to indicate all possible value of inputs, since I have 3 inputs, is to create 8 rows and go through the values 0 to 7 using 3 bits like we were counting in octal. So I'm going to have all zeros initially, and then I'll have a 1, and then I'll have a 2, etc. So now I have completed entering all the rows, and if you just take a look, we've just simply counted from 0 to 7. This represents all possible inputs. Now you can call the next 2 columns, I'm going to call them intermediate columns because they're in between the input and the output of X. So I could call them D since the diagram indicates D, or I could call them A and B and A and C. Finally, the last column is X. So here are my inputs. These are my intermediate columns, which you can think of as D and E, and here is my output. And now I'm going to determine the intermediate values, which are D, A and B is D, and A and C is E. Okay, 0 and 0, right here, 0 and 0, 0 and 1. Now I'm going to look down, and the only time I have 2 ones are these last 2 rows, right? And so the rest will be zeros. Repeat the same thing for A and C. I got 0 and 0, 0 and 1, 0 and 0, 0 and 1, 1 and 0, 1 and 1. So A is 1, C is 1. I get a 1 here. 1 and 0, and 1 and 1. Finally, the output, which is my X, is doing an OR of the 2 intermediate values. If you recall, then whenever you have a 1 in at least one of the columns, you're going to get a 1. And if both columns are 0, then X will be 0. So you should be able to look at a combinatorial circuit such as this and determine what the Boolean expression is, and also determine what the truth table is. So in this example, the author gives us this expression, And you will do what's inside the parenthesis first, which is an or, okay? Remember the author does a plus sign for the or. So we're going to take our inputs B and C, and we're going to OR it. And there it is. There's that gate, okay? B or C. Now the output for B or C is then being ANDed. So this is an implied operation. It's kind of like multiplication. Personally, I would prefer to write A and parentheses B or C. That's the way I would write it. But, so now the A is being ANDed with the results of B or C, and there is our output, which I like to call X. So you should be able to go from the Boolean expression to the logic diagram. And can you go from the Boolean expression to the truth table? Once again, we have three inputs, A, B, and C. So here are our input columns, and here is the intermediate column, and here is finally our output column. And again, you will do the intermediate column first, where we're ORing B and C. Anytime you see a 1, you see that B or C is 1. Then we'll take the result of this and we'll AND it with that to produce our output here. So we're ANDing, of course, whenever you're ANDing, both operands need to be 1. So here we have 1, and here we have 1, and here we have 1. And this truth table is exactly the same as this one, which was called by an entirely different circuit. So these are called circuit equivalents. It is possible to have the same output given the same input and yet construct the circuit in two different ways. In fact, what you see there is actually an application of some law shown on page 107. This is the distributive law. It looks just like the distributive law you probably learned in mathematics. So some of the properties or some of the laws that you learned when you were in mathematics applies also to Boolean algebra. The commutative law, associative, distributive, identity, and complement. What may be new to you is De Morgan's law. And De Morgan's law says that if you take A and B and not it, A is equivalent to A not or B not. You can also write this as A or B, then not it is the same as A not and B not. That's the De Morgan's law. So what kind of practical circuits can we create? And one simple circuit is known as the adder. So you learned in the last unit that 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 1 equals 0, carry 1. Okay, so can we create a circuit that does that? Given those inputs, we'll always produce that output. And that's called an adder. So our author started by creating the truth table. So here is the truth table of those four possible additions. And we actually have two outputs, the sum and we have the carry. Because 1 plus 1 is 0, carry 1. Leading to an additional output. So the first circuit we're going to look at is the half adder. So the half adder sums 2 bits and produces this output. Let's see what it looks like. Okay, so the half adder will take 2 inputs, A and B. Now, because there are 2 inputs, there will only be 4 rows, just like what we have here. That's all possible combinations. Why only 4 rows? Well, there's 2 inputs, 2 to the power of 2 equals 4. When there's 3 inputs, we had 8 rows. 2 to the power of 3 equals 8. That input is being summed. Now let's think of this. So if we have a 0 here and we have a 0 here, what's the sum? 0. If we have a 1 here and we have a 0 here, what's the sum? 1. Now let's think. 0 exclusive or 0 is 0. 1 exclusive or 0 is 1. 0 exclusive or 1 is 1. 1 exclusive or 1 is 0. And that's exactly what we have here. Okay, that seems to work. Now those 2 same inputs are going into our AND gate. So if you take a look at this output, this is the output of an AND gate. So this is our half adder. But what about when we carry? So if you do a carry, we then have a third input column. That's our carry in column. We now have still the sum column, and we'll call the other carry the carry out column. So we still have two inputs. And so it looks like we've got a half adder, and we got another half adder. And the results of both of these half adder determines the carry out, and that is our full adder. So what we were looking at earlier is called combinatorial circuits, and those circuits, the output is determined solely by the input. But how does memory work? Memory in RAM, once I give it a 1, it has to stay a 1. Imagine you have an image, right? And that 1 sometimes becomes a 0 and becomes a 1 again. And you have thousands of bits doing that. That image will not stay on the screen. So once you assign a value to RAM, it needs to stay that value until you clear it out. And that is what a sequential circuit does. That needs a sequential circuit. Is it 1? Can I keep it 1? Can I keep it 1? So let's take a look at what's called the SR latch. The SR latch is what can be used for RAM. Notice that the state of this output is being fed into this NAND gate, and S stands for set and reset. Once you send a 1 in here to set it, it stays at 1. I don't need to send anything else here. It just, the way this is set up, it stays at 1 until a reset hits. Reset means, okay, pull it back to 0. To get a better explanation of the SR latch, take a look at this video, Introduction to Digital Electronics, on the SR latch. That about sums up the depth that we're going to go into circuits, but I hope you understand that transistor make gates, gates makes circuits, circuits are responsible for the processing that's done in the CPU. It's responsible for being able to hold the data that we put into memory. Circuits are responsible for what we call integrated circuit chip. It's the chip that we put on our motherboard. Historically, we have gone through many variations of the scale, the number of gates we can put on a chip, and this is related again to Moore's law, and right now we're right here in the very large scale integrated circuit chips. In fact, in 2014 there were chips with over 20 billion transistors. That wraps up our concepts, reviewing gates, logic gates. Learning Boolean expressions is an important part of programming, and we will be addressing it more and more during the semester.